Hi everyone, I'm Laura Batterink. Today I'll be sharing my research with you on the developmental trajectory of statistical learning using an EEG-based measure of neural entrainment. I want to thank the organizers for inviting me today and organizing this great panel. To understand spoken language, a language learner needs to decompose a continuous complex audio signal into its constituent meaningful units and thereby extract meaning. To do this, we really need to become sensitive to many types of temporal patterns that exist in this signal. Statistical learning is the ability to pick up on patterns and input through passive exposure, and is thought to play an important role in many aspects of language acquisition. The above waveform represents a spoken sentence, "Someone somewhere wants a letter from you." To decode this sentence and successfully extract its meaning, we need to be able to pick up on different patterns that exist in this signal. These patterns exist at multiple levels and also interact with one another. For example, the co-occurrences between neighboring syllables or transitional probabilities are higher within a word than across a word, and becoming sensitive to these types of cues may be one way that language learners can segment speech or break up continuous speech into its component words. In addition, there are many other types of regularities in language, such as vocabulary, which involves mapping word forms onto objects or concepts in the real world, and syntax, which involves picking up on the rules and regularities that govern how different words can be combined and in which order they can be combined in. An important theoretical question about statistical learning is whether and how it differs across development. And while statistical learning plays a role across many different aspects of cognition, here I'll be focusing on the role of statistical learning in word segmentation. So if we consider the relationship between statistical learning and age, there are a number of basic possibilities that could be true. One is that statistical learning may decline with age, similar to many other aspects of language acquisition. A second possibility is that statistical learning could improve with age, consistent with other aspects of cognition, such as attention and working memory. And then finally, a third possibility may be that statistical learning is age invariant and shows stability across the lifespan. What we do already know about statistical learning in the context of development is that it has been observed across different ages. So as you know, this ability was first reported by Jenny Safran and colleagues in her seminal study on infants. And soon after this, it was also reported by this group that both 6 to 7-year-old children as well as adults also showed this ability to do statistical learning. More recently, Inbal Arnon has also demonstrated this ability to do statistical learning in word segmentation in age groups spanning 6 years to 12 years. So although statistical learning has been observed within different age groups, there haven't been many studies to compare statistical learning across different ages. And one important reason for this lack of direct age group comparisons is the methods that are used to assess statistical learning. So in the lab, statistical learning is typically studied by exposing participants to a continuous stream of repeating nonsense words. You may be familiar with this stream already, but it sounds something like this. So this learning is typically assessed using some kind of offline task that's administered after the exposure period. And this is where the two procedures really start to differ depending on which age group it is that you're looking at. So in infants, the typical way that this is assessed is using some kind of preferential looking time paradigm. And in contrast with older children and adults, this statistical learning is usually assessed with some kind of explicit recognition judgment. So in both cases, statistical learning is inferred based on performance on these post-exposure tests. And so while we can say that infants are learning or that children and adults are learning, we can't easily compare performance across these two types of tests. And even between children and adults who are tested using the same measure, these comparisons may be problematic. So although this is a relatively simple test, if we break it down, we see that it does require some other domain general abilities. So children, for example, must understand the task instructions. They need to successfully listen to both items in the test. They need to make a decision about which is more familiar based on their exposure to the language. And then finally, they need to choose an appropriate button response. So even if children do succeed at performing on this task at equal levels to adults, it's possible that their performance on this task may actually be an underestimate of their true statistical learning ability. So essentially, because of these different methods of assessing statistical learning, we have separate literatures, and it's difficult to directly compare performance across these different groups. In contrast, if we had an online measure that captured statistical learning more directly, it would be easier to compare performance across development. It would allow us to look at statistical learning across the lifespan as a continuum and bridge this gap between the infant literature and the literature concerning older children and adults. And in addition, an online measure could also reveal the time course of learning. And finally, at a more theoretical level, capturing learning online using some kind of neural measure could reflect a more pure assessment of learning that's not being contaminated by post-learning processes such as decision-making, memory retrieval, memory performance, etc. So one way that we and others have been able to look at statistical learning directly is by measuring neural entrainment during the learning procedure. And this tool takes advantage of the neural steady state response. The steady state response is a tendency for brain activity to resonate or oscillate at the same frequency as an ongoing rhythmic stimulus. So for example, as shown in this very early EEG study here, in response to a regular flicker of light, EEG recorded from sensors over visual areas shows a response at that same flicker rhythm. And the really nice thing about neural entrainment is that it's not simply reflecting bottom-up sensory processing. It's not just sensitive to low-level acoustic features of an auditory signal, for example, but it's also sensitive to top-down processes that are driven, for example, by your perception of a stimulus as driven by top-down knowledge. This neural steady state response can be applied to statistical learning by presenting auditory stimuli such as syllables at a steady rhythmic rate. So if we do this, what we expect to see is a neural steady state response at the syllable presentation rate. So in this case, 3.3 hertz. Now, to the extent that somebody being exposed to a stream like this is picking up on the underlying structure of the stream, what we additionally expect is another neural response at that corresponding word rate. So in this case, 1.1 hertz. And further, we might expect that over time, as somebody becomes increasingly sensitive to the statistical structure of the stream, we would see a shift in entrainment towards the word rate and away from the syllable rate. As their perception becomes dominated by the underlying words, they're perceiving the individual syllables less and less. And we might also expect that this measure should be sensitive to individual differences in learning. So a good learner may show relatively higher word level entrainment, whereas a poorer learner may show relatively higher syllable level entrainment. So in our first study, we tested whether this method of EEG neural entrainment could be used to assess statistical learning. And this was done in adults. So we presented learners with a random condition in which the syllables did not follow an underlying pattern. Here we expect to see relatively stronger syllable entrainment. And we also presented them with a typical structured condition as in a normal statistical learning task. So here there's a repeating trisyllabic structure. And if they pick up on this structure, what we expect to see is an increase in word level entrainment and a decrease in syllable entrainment. So here's a graph showing the neural entrainment results to both of these types of streams. Frequency here is on the x-axis, and entrainment or intertrial coherence here is on the y-axis. And in addition, the structured stream is shown in red and the random stream is shown in blue. So what we see is an increase in word frequency entrainment for the structured condition compared to the random condition. And in addition, we see a decrease in the syllable level entrainment in the structured condition as compared to the random condition. In addition, we also found that these entrainment signals shifted over exposure consistent with what we expected. So in the red condition, the structured condition, we see an increase in neural entrainment at the word frequency and a corresponding decrease in neural entrainment at the syllable frequency as the exposure continues over time. And we don't see this same shift in entrainment for the random condition. And then finally, we also found that the ratio of word frequency entrainment to syllable frequency entrainment, which we quantified using a word learning index, predicts performance on post-learning tasks, specifically a reaction time-based task that assesses participants' ability to implicitly predict upcoming syllables. So together, what these results show is that neural entrainment can effectively index statistical learning online. It distinguishes between structured and random input, it tracks learning over time, and it's also sensitive to individual differences in statistical learning. So altogether, these results suggest that neural entrainment reflects the real-time changes in linguistic representations that are accrued during learning. Because we now have a way to look at real-time statistical learning without needing to rely on behavior, we can now more directly compare statistical learning across different ages in development. So in the first study that we ran looking at the development of statistical learning, we examined a group of 6-month-old infants. And all of this work was done in collaboration with Daewon Choi, Alexis Black, and Janet Worker at UBC. Infants were exposed to a typical statistical learning stream composed of repeating trisyllabic words while their EEG was recorded. And then they also performed a typical looking time test after this exposure period in order to assess whether they showed a typical novelty preference. That is, whether they preferred to listen to non-words as opposed to words that they were already familiar with from the exposure stream. And so we're really looking at two related questions here. One is whether we can use this method to index statistical learning in infants. And then secondly, if that is possible, whether there's evidence that statistical learning differs between these 6-month-old infants and the adults. So even though we're dealing with noisy, wiggly infants, what we see is the same sort of neural entrainment response that we saw in the adult. So here what we find is, again, a peak in neural entrainment at the word frequency as well as at the syllable frequency. And for comparison, this is what the effect looks like in the first study that I presented. So this highlights that this approach, this frequency tagging approach, has very good signal to noise ratio because we're getting a similar looking response even though the infant's data is typically much noisier than the adult's data. At the behavioral level, we replicated the novelty preference that is most often found in the developmental literature. So the infants preferred to listen to non-words. They were more interested in the non-words as opposed to the words from the speech stream. And interestingly, their novelty preference, the extent to which they preferred to listen to novel words, was predicted by their neural entrainment value. So the infants that showed stronger word level entrainment compared to syllable level entrainment showed a greater novelty preference. So one of our key predictions was that we would see a significant increase in the word learning index over time. And this would reflect an increase in infant sensitivity to the statistical structure of the language. And in fact, that is what we find. So the infants are shown here in red, and using a moving time course analysis, what we see is that relative word level entrainment increases, particularly over the first 100 word exposures or so. And so this is a significant logarithmic increase. Interestingly, when we did the same analysis in adults, we did not see a significant group difference. So the infants and adults followed a very similar learning trajectory. So when we directly compare neural entrainment between the infants and adults, we don't find evidence of a different learning trajectory over time. And so the tentative conclusion based on this one comparison is that statistical learning may be a learning mechanism that emerges early in life and that shows stability throughout the lifespan. So in a second study, we looked to extend these results into a middle age range, so looking at children. And this study was done in collaboration with colleagues at Western, so Christine Moreau, who's a PhD student, as well as Mark Jonice. And in this study, we specifically looked at 6 to 12-year-old children. And so at the behavioral level, we replicated some of the previous findings that I mentioned at the beginning of my talk. So essentially, children and adults did not show significant differences in performance across 3 behavioral tests that we administered after the exposure period. So on the recognition task, on an explicit rating task where they're asked to rate individual words for their overall familiarity, as well as on a reaction time-based measure, the target detection task, we don't see significant learning differences between adults and children. Adults did respond faster on the target detection task here, but the facilitation, so that's the difference between response time for the first syllable position compared to the more predictable third syllable position, that facilitation effect was not different. However, there was a marginal correlation within the children's group whereby older children performed slightly better than younger children. But interestingly, even though we don't see differences between children and adults at the behavioral level, we do see differences in neural entrainment. So what we can see here is the same entrainment plot with adults shown in blue and children shown in red. And children showed significantly stronger neural entrainment than adults at both the word and the syllable frequency. And this enhanced word level entrainment tentatively suggests that they may be discovering the underlying word patterns more successfully or at higher rates than the adults. In addition, within the children's group, we again validated this measure. So neural entrainment predicted 2 of the 3 post-learning tasks that we administered. The word level entrainment correlated with both performance on the rating task as well as what's shown here, the reaction time effect on the target detection task. And then finally, we did a similar time course analysis to the one that I described for the infant study. And what this time course analysis indicates is that the children are showing stronger increases in neural entrainment to the word frequency compared to adults. So the children are shown here in red, and this increase over time, there's an increase for both adults and children, but it's significantly stronger for the children. So what this result suggests is that children may be gaining sensitivity to the structure of this artificial language more rapidly than the adults. So although we didn't find evidence of a difference in statistical learning between the infants and the adults, between the children and the adults, we do see a difference, suggesting that the children show stronger sensitivity to the statistical structure of the language and suggesting a possible advantage for learning in children. So here's a kind of cartoon summary of what we see across these different studies. These results point to relatively stable statistical learning across the lifespan, but with a possible peak in childhood between this 8 to 12 range. And this peak in childhood may have been masked by behavioral tests used by prior studies, but it may be revealed by using more sensitive neural measures that don't necessarily depend on behavior and that don't perhaps disadvantage children because they're less adept at performing the behavioral tests. So of course there are many caveats. This cartoon is obviously a very oversimplified description of the data. We've only measured statistical learning at these 3 discrete time points, so we don't really have the full understanding of how this changes across these different ages completely, but these are what the results so far seem to be suggesting. So this overall developmental picture supports the idea that statistical learning is an ability that's comprised of multiple components. And each of these components may have their own developmental profile and possibly a unique sensitive period. In their recent review, Janet Worker and Taco Hench proposed that there are multiple cascading and interacting sensitive periods that underlie the learning of speech during infancy. So similarly, there may be multiple processes that each have their own developmental profile that are contributing to statistical learning as a whole. So one explanation for this U-shaped curve may be that some underlying processes that contribute to statistical learning in 6-month-olds are not yet fully developed. And that's why we see roughly equivalent performance between the 6-month-olds and the adults. So for example, perhaps phoneme perception in their native language, we know that continues to mature until 10 to 12 months of age. That's not likely to be fully online yet. And also domain general processes such as attention, working memory, declarative forms of long-term memory. These are all immature in the 6-month-old infants, which could be driving down their overall ability to do statistical learning. In contrast, other components may show a decline with age, and this could explain why the children are actually showing better performance than the adults on overall statistical learning ability. So with increasing age, speakers of a given language may become increasingly resistant to learning new information that conflicts with their native language. In children, the relevant neural networks that underlie the learning of new phonotactic information or new phonotactic patterns may not yet have fully committed to the native language, and this may allow them to be more open or more easily able to absorb new patterns that are present in the statistical learning stream. So returning to the 3 possible curves that I described in the introduction, overall these results suggest that there is some kind of decline in statistical learning ability, at least between childhood to adulthood. And this would parallel the well-documented effects of age of acquisition on ultimate language attainment, where adults are typically unable to attain the same ultimate level of proficiency in all aspects of language. So I'll just wrap up by thanking my collaborators on these different projects. The developmental work in particular couldn't have been done without these great collaborators. And I'll also thank my sources of funding, and thank you for your attention.